Good morning, everybody. Today's lecture is about chapter 19, or ionic equilibrium in aqueous systems. So basically, we are looking at the effect of the equilibrium established by the ion dissociation within the aqueous environment. Um, Now, before we go any further, we need to define some basic terms and concepts which will be useful to us throughout the chapter. The first term that we need to define is buffer. A buffer, by definition, is made of a weak acid and its salt, and a weak base, or a weak base and its salt. So for a weak acid and its salt, for example, we can mix acetic acid, or CH3COOH, and the salt of that, which is something like sodium acetate, CH3COONA. So we are removing this hydrogen and replacing it with a metal to form the salt. So this is the weak acid, this is the salt of that weak acid, and therefore the combination is a buffer. Or you could have a weak base and the salt of that weak base, in this case ammonia and ammonium chloride, to form your buffer. The buffer has this characteristic that it resists a change in pH when we add small amounts of strong acids or strong bases to it. So that's the main characteristic of a buffer system. This is the recipe how to make it. Basically, you take a weak acid and mix it with the salt of that weak acid, or you take a weak base and mix it with the salt of that weak base, and therefore you have the recipe of how to make the buffer. But the second statement here, it's about the way the buffer works, or its main characteristic, which is to resist the change in pH after you add small amounts of acid or base. Now, I have underlined the word small because if you add a large amount of a strong acid or strong base, the pH of the buffer will not remain the same, and it will change. But it has to be a small amount, and we will demonstrate that by some examples as we progress through this lecture. The second term that I wanted you to learn about is called the common ion effect. The common ion effect, which is actually is explained in section 18.1 in your textbook. But it basically occurs when a common ion is added to an equilibrium mixture that already contains that ion, and the position of the equilibrium shifts away from forming it. Table 19.1 on page 844 basically shows you how the common ion effect works by looking at different percent dissociation of the acetic acid that is reduced by adding the salt, or an anion, CH3CO minus, to the acid. Now, as you can see, the CH3CO minus, which is the common ion, is added to an aqueous solution of the acetic acid. So this common ion is going to reduce the ionization, or reduce the percent dissociation of the acid. Again, this is just a basic introductory definition of what common ion effect is. We will take a look at more details of the common ion effect when it comes to calculating different properties of the common ion effect, or properties that are affected by this effect. But usually with the common ion effect, we will have an ion that has something in common with the weak electrolytes that we are studying. For example, in this case, the weak electrolyte being the weak acid here, and we add to it a common ion. Well, it could be H plus or CH3CO minus, but in this case, the acetate ion works better. So we are adding the acetate ion to this, to the weak acid. And then we are looking at how the ionization of this acid is changed by this addition. And usually the way it works is that through the Le Chatelier principle, the ionization is suppressed. So in other words, instead of producing more of the ions on the right-hand side, the ionization is shifted to the left. So that is demonstrated in table 19.1. As I said, again, we will come back to this later. If you don't see the full picture right now, it's okay. I just want you to be introduced to this term, common ion effect. This is the definition, and this is an example of how it works. Okay, but we will come back to it and study it in more detail later on. Okay, now let's go back. Let's go to the next slide. Let me see. This is the next slide. Okay, so this sample problem 19.1 on page 846, it basically shows us how to work with a buffer system and calculate the pH of a buffer system, because we are mainly concerned about the calculation of pH when it comes to buffer systems. Not only that, we also want to know what happens when we add a small amount of strong acid or strong base to that buffer system. What happens to the pH of that buffer system, okay? So part A deals with the calculation of pH for a buffer system which is made of a weak acid, HClO, and the salt of that weak acid, sodium NaClO, which is the salt of that. Okay, so we have a mixture of weak acid and a salt, therefore we have a buffer. The first question is, how do you calculate the pH of this buffer system? The second question, part B, is if we add 0.02 mole of sodium hydroxide, which is a small amount of a strong base, to the 1 liter of the buffer system, how the pH is going to change compared to part A, which is a pure buffer. And part C is if we add a small amount of a strong acid instead of a base to 0.5 liter of the buffer, how is the pH going to change again compared to part A? So part A is kind of the standard or the control system for us, the standard system. And part B and C, the pH will be compared with part A. So part A, now how do we calculate the pH of any buffer system? That's an excellent question, because we will be referring to this again in later parts in the chapter. But right now we are going to use the equation called the Henderson-Hasselbalch equation, or the HH equation, to calculate, which is placed in this red box here, to calculate the pH of any buffer system. So the HH equation, or Henderson-Hasselbalch equation, states that the pH of a buffer is pKa, which is equal to the negative log of Ka, plus the log of the base coming from the salt divided by the concentration of the acid. Okay, so this simple, useful equation is worth memorizing, and it's known as the HH, or the Henderson-Hasselbalch equation. Okay, so we're going to use this Henderson-Hasselbalch equation to work out the pH of the buffer for part A. So for part A, the pH will be the pKa, which is basically the negative log of Ka. pKa is negative log of Ka. The Ka is given to us in the problem. And we take the negative log, and that's 7.54. Okay? And then the concentration of the base is 0.6. The concentration of the acid is 0.5. We plug it in. We take the log of the ratio. We add it to 7.54, and we get 7.62. Okay, so that is where all other pH is going to be compared with. So this is the pH of just the buffer itself. Now, we have not added a base or an acid yet, and we will do that in parts B and C for this problem. Okay, so now let me just move this a little bit to the left. Okay, now we are going to add some sodium hydroxide to the buffer, and see how the pH of the buffer is going to change compared to 7.62 that we have here. So now, first of all, when we are dealing with the addition of a base or an acid to the buffer, we always have to set up a table. Now, this table is not the equilibrium table, but it's very similar to the ICE table that we use in the equilibrium concept. Instead of ICE, we have ICF now, initial, change, final. Okay, so again, this is not an equilibrium problem. It's just a simple reaction between the acid part of the buffer, which is HClO, and the base, which has been added, OH minus. Now, it's useful for us when it comes to the addition of acid or bases to the buffer system and to this ICF table. It's useful to have the quantities converted from moles or liters to molarity. So basically, we want to work with molar quantities or molar concentrations in the ICF table. So the concentration of the acid given in part A is 0.5. The concentration of the base can be calculated here. It's 0.02. Initially, we don't have any ClO minus. Water is constant. Nothing for water. And then the change. Now, so initially we have two quantities, 0.5 and 0.02, right? Okay, now when it comes to change, the change is going to be the negative of the smaller quantity of the pair, which is, if you remember from General Chemistry 1 or Chem 107, we call it the limiting reagent. The limiting reagent is the smaller number of the member of the pair, which is OH minus here. So negative of 0.02, negative of 0.02. And then, of course, on the other side, on the product side, it's going to be plus 0.02, right? And then we add the I to C to get F. So this is very similar to the concept of the ICE table, the ICE table, but with one exception, that we don't have equilibrium here. Okay, but again, we will always be concerned with the final quantities. Okay, now at the end, as you can see, you can have HClO left as 0.48 and ClO minus as 0.62. Now, this is a combination now in the final stage of 0.48 molar weak acid and 0.62 molar the salt of that, or the base of that weak acid, and therefore, by definition, it's a buffer system, and we use the Henderson-Hasselbalch equation again to calculate the pH of that buffer. Now, what's important about this calculation is to compare it with the original buffer pH, which was 7.62. So as you can see, it went from 7.62 to 7.65, which for all practical purposes, we can say the pH almost remained constant. Okay? So again, remember, one of the main characteristics of a buffer system is that the pH doesn't change drastically if we add small amounts of strong base or strong acid, as it's demonstrated from going from 7.62 to 7.65. Now, in the next slide, we're going to be looking at the addition of a small amount of HCl to the buffer system. Okay. Now, so what we need to do is to basically realize that the H plus from HCl is now going to react with ClO minus component of the buffer. Remember, buffer is made of HCl O plus ClO minus. So the ClO minus component of that buffer is going to react with H plus from HCl. Okay, and the reaction is written here. H plus from HCl reacting with ClO minus. But before we actually set up the ICF table again, we need to recalculate these concentrations. So, in other words, when you write this reaction, ClO minus plus H plus to give you HClO plus water, now we need to ask the question, what are the initial concentrations? The initial concentrations are now different. So I have calculated the HClO, ClO minus H plus concentration. So basically, the mole, for example, for HClO, the moles of HClO divided by the total volume. The moles is 0.5 molar times 0.5 liter. Again, everything here is given to us. Divided by the total volume, which is 0.53. Now, how do we get 0.53? 0.5 liter of the buffer, 0.03 liter is added, so that brings up the volume to be 0.53 as the total volume. Okay, so we do the same thing for the other components. And again, all these quantities that I'm using here are given to us in the problem. All I'm doing is I'm recalculating these concentrations. Okay, so this is the reaction with the numbers coming from here. The initial quantities are given. The change will be the smaller number of the pair, which is 0.085, and final numbers can be calculated easily. And again, as you can see, we have the acid in the final stage. We have the acid left, and none of the the HClO as the weak acid left. The strong acid will be consumed completely. Nothing of the strong acid HCl will remain, and we have the base or the salt of that weak acid. So we have a weak acid and its salt. Therefore, that mixture is by definition a buffer system. And now we have to use the Henderson-Hasselbalch equation one more time to calculate the pH of this system, where we have 0.56 molar HClO, 0.48 ClO minus. And in the next slide, we can see that the HH equation can be used now to calculate the pH, and we plug in the numbers and we get 7.47. Now again, compared to the original pH of the buffer, this is not a drastic change. So therefore, we can say safely that the a buffer has acted properly and has not created a big shift or big change in the pH after we have added the HCl to it. Okay, so this is a basic calculation on buffer system. First, we calculated the pH of the buffer by itself, and then we calculated the pH of a buffer when we added the small amount of OH minus, and then in part C, we recalculated the pH once we've added a small amount of HCl. Okay, so you need to know how to calculate all those three different, how to work with those three different pH calculations. Okay, now the next topic is dealing with something called weak acid strong base titration. Okay, that is actually on page 855 in your textbook. Now, the best way to illustrate this weak acid strong base titration is by an excellent example in the book, sample problem 19.4, page 557. So basically what we have now is we are reacting or we are adding a strong base to a weak acid, okay? And the name of that is basically, another name for it is a titration reaction, when we have a reaction between a base and an acid. So the question is, if you add, for example, 30 milliliters, 40 milliliters, or 50 milliliters of this base, which is 0.1 molar, a strong base, to the acid, which we already have here as 0.1 molar propanoic acid, HPR, and we have 40 milliliters of it. So if you have these different volumes of the base added to this acid, how is the pH going to change? What is the pH after each addition? So in other words, for example, here I add 30 milliliters of the base. What is the pH? I add 40 milliliters of the base to the acid. What is the pH? I add 50 milliliters. So when we change the volume of the base and we add different volumes of the base to that fixed amount of acid, the pH will change. And the question is, how do we calculate that pH? Okay? So part A is easy. Part A is very easy because we have not added any base to that acid. And the question is, we have 40 milliliters of 0.1 molar HBr. The K is given. What is the pH of that? And if you remember, the shortcut to calculate the H plus is the square root of Ka times the concentration of the acid. So that's basically 1.3 times the negative 5 times 0.1. Take the square root, you get 1.1 times the negative 3. So the pH is negative log of that, and that gives us 2.96. So this is the pH of 0.1 molar HBr before we add any sodium hydroxide to it. Now, part B, we are going to add 30 milliliters of sodium hydroxide. We have to write a reaction. We have to recalculate the concentrations, the moles, and calculate the pH again, which is demonstrated in the next page. So here, I have indicated that for acid-base titration reactions, it's more useful to use moles, not concentrations, because we are constantly changing the volume of the component that is being added, or the titrant. So in this case, we are constantly changing the volume of the sodium hydroxide. So therefore, the number of moles, which is constant, is going to be divided by a different number as we progress through the titration. So therefore, we always need to know the moles of different quantities. And so what I'm trying to say is that in acid-base titration reactions, we always we set up the ICF table again. Remember, this is not an equilibrium reaction. Again, it's a reaction between acid and the base, but we have to use moles instead of concentrations because we keep changing the volume of the titrant. Okay, so I have calculated the moles of HBr, the moles of OH minus. Again, these are all outlined in your textbook. So 0.04 liter times 0.1 gives you the moles. 0.03 liters times 0.1 gives you the moles of OH minus. So initially, we write the reaction as HPr plus OH minus, giving you PR minus plus H2O. The change is going to be the smaller number of the pair, negative of that. And then at the final stage, we have 0.01 HPr, 0.03 PR minus. We immediately recognize that as a buffer system. We calculate it through the Henderson-Hasselbalch equation. But remember, when you calculate everything is given, so there is no need for me to go through this part again. It's self-explanatory. But the volumes, remember, this is concentration now. It's not moles. So PR minus is going to be what? The moles of PR minus divided by the total volume. 0.03 total volume is what? Total volume is 40 milliliters plus 30 milliliters, which is 70, which is 0.07. Now, the volumes will cancel out. So you might as well write it as just this number, 0.03 divided by 0.01. So that's like simplify the problem. So 0.07 cancels 0.07. So therefore, the pH becomes 5.37. Okay, so this is part B. Now for part C, we still have a different volume of that. Now, part C, we are adding an equal volume as the original acid. Okay, so in part C, we are at the equivalence point of the titration. The equivalence point is defined as when the number of moles of acid reacting is the same as the number of moles of base that is being added to that acid. So in other words, equal moles of acid react with equal moles of base. Okay? And the reaction is outlined here. Again, 0.04 moles of HPr reacts with 0.04 moles of OH minus. Nothing here, this is constant. So if you take the negative of the, we don't have a smaller quantity, so basically we end up 0, 0 for both reacting components, so they completely neutralize each other, and what we get at the end is 0.004 moles of Pr minus, which is the salt. So at the final stage, or in here F, only Pr minus remains. So now Pr minus acts as a base or a salt because it's negatively charged, and we calculate its concentration to be 0.05 molar. And now the question becomes, how do you calculate the pH of a 0.05 molar Pr minus solution, which is a salt solution? And if you remember from the shortcut, the concentration of OH minus for any salt solution is going to be Kb times the concentration of the salt. Take the square root, but the Kb has to be calculated. Again, go back to the calculation of pH for a salt. The Kb has to be calculated, and that is 1 times 10 negative 14 divided by Ka. K is given, so we plug in everything in this equation, and we get the pOH. Remember, this is the concentration of OH minus, so we get the pOH, and 14 minus pOH will give us the pH. Now, for the last part of this problem, we are adding 50 milliliters of sodium hydroxide. Again, we recalculate the number of moles. The moles of HPr is constant, is always 0.04, but OH minus that is being added is every time we change the volume is going to have a different number of moles. So now it's 50 milliliters, so it's 0.05 liters times 0.1, and then we set up the equation again, the reaction again. So now we have more OH minus compared to the acid. So OH minus is in excess. HPr is the limiting reagent. So we go through the calculation again, and at the end we have 2 bases left. Pr minus 0.04, OH minus 0.01. But the question now becomes, which base will be the stronger base to dominate and therefore determine the pH of the solution? And the answer is OH minus coming from sodium hydroxide is a much stronger base compared to Pr minus coming from HPr, which is a weak acid. Okay, so therefore so anytime you're left with OH minus and some other base in your reaction table, always choose OH minus as the one that will dominate. So the OH minus is going to be 0.01. The concentration of that is going to be 0.01 divided by total volume. The total volume is 40 milliliters of the base of the acid that you start with, and 50 milliliters of the base that you're adding. So therefore, that's the total volume, and then you can calculate the pOH and pH subsequently. So the pH is going to be, of course, basic because you have more base compared to the acid to begin with in the reaction. Okay, so I hope, I know I have given you a lot of equations and calculations and a lot of concepts to work with here in this presentation, but unfortunately that's how things progress, because now we are getting into more advanced topics of acid-base titrations and also buffer systems, which are considered to be advanced. Now, please work on the follow-up problems at the end of each sample exercise that I've presented here. So I've basically given you 2 sample exercises, but there are more follow-up problems that you can work on your own free time. And Please take a look at the book and go through these examples. If you have any questions, let me know by this Thursday when we meet again at 11 a.m. Okay? Have a great day, and I will see you this Thursday at 11.